thank you everyone for joining us for the last workshop of the day. On behalf of the organizers, I hope you had a solar experience today. And what better way to close the day than with a workshop dedicated to closing the proverbial loop of PV and recycling systems. Now, when we prepared this workshop, we had quite a lot of discussions on why we need a dedicated session to PV and PV recycling. Well, that's because we are at a point in time where where energy security and climate change are converging into a singular point, and that is energy transition. And solar is now at the forefront of this change that is happening, of this massive shift, which is also, that's why we have the name Power Shift for the event. We have now a tangible, yeah, sure, you can join us. I was waiting to call you, you know. It's all right, it's all right, it's all right. So we have this very tangible target of 600 gigawatts by 2030. You will also see the target of 750 is the same, but in different ways of measuring the current. The fleet of the Solar Union is growing rapidly, and it is on its third year of double-digit growth, and is not showing signs of stopping. And yet we have this massive number of PV panels that are entering the market, but no real solutions on how and what we'll do once they will reach their end of life. Now, we don't have, unfortunately, a dedicated piece of legislation that tackles the processes that should be taken into account when recycling and reintegrating PV panels into the system, and that's what we're going to discuss in the next 40 to 45 minutes. I'm joined by a solar lineup of speakers. We have with us Carlos, we have with us Daniela, and also Rune and Duygu, who will be joining us online. And we will try to tackle and try to explain why this need of recycling and reintegrating renewable PV panels into new production cycles. Now, as I've mentioned, we don't have a dedicated piece of legislation that's going to cover what's happening with panels at their end of life. And I would like to ask you, Daniela, can you explain a bit what's happening, what is the current practice, and what should be done?
Indeed. Thank you for the word. So for everyone, my name is Daniela Blažejová from SolarPower Europe, and I am a project coordinator involved in a couple of EU projects that tackle recycling. And you can also meet me on the meetings of the product sustainability workstream that I also coordinate. So today I'm gonna tell you a little bit about what are the challenges and opportunities in PV recycling, what is currently being done, and what can be done better. So I also have a couple slides, but I don't think, oh yeah, there they are. Okay, so I might actually stand up. Okay, so the first question is what happens to PV modules at the end of their life cycle? So we can say that PV modules are highly recyclable with technical recycling rates of 90% or beyond. However, it is important to ask what is being recovered and how is it being recovered, because that question will tell us then a little bit more about the details and about what are the challenges in the sector. So currently, this is how a typical crystalline silicon PV module looks like and what is the percentage of the materials by weight. So there you can see that 70% of the module is glass. Then we have aluminium, plastic, silicon, copper, silver, and then a small percentage of high-value materials such as gallium and indium. And I already circled those that are currently being recycled. So you see that the glass is usually recycled, the aluminium, and then the plastics, and then from the cables, the copper is recovered. But you can also see what is not being recycled, that commonly, which is silicon and silver and all these tiny, tiny materials. So to walk you through a little bit through the common recycling process. Now I'm not a technical person, so if there's somebody who wants to correct me, feel free. But this is just generally what is being done to the PV module. So first of all, the junction box, the cables and aluminium frame are manually separated, and then the copper can be recovered, the aluminium from the frame is recovered, and plastic is most commonly incinerated. And then solar glass is removed with delamination techniques. It can be a mechanical technique, thermal or chemical technique. And then the recovered materials are purified further. So from that process, you can see that currently the silicon is not being recovered, but also silver is not recovered, and silver has a very high value, which you can see on the second pie chart over there. That silver is only 0.07% of the PV module weight, but it is actually almost 50% of its value. So that is a huge economic opportunity that we are currently missing. Plus there are other high-value materials in the module, such as indium. When we talk about glass, we say that glass is being recycled. However, currently the glass is not up to the highest purity it can be. Therefore, its applications are also very limited. So it can be used as a technical glass, but not as flat glass, not as packaging glass, etc. So yeah, the applications are very limited, and there is an opportunity for doing better. Next to the economic benefits and the environmental benefits of recycling, we also have a big stream of critical raw materials that we have in Europe, and that we could recover from these modules instead of sourcing them from out of Europe. So it is also an opportunity for sourcing domestically. In general, what are the challenges in recycling? There are many different PV modules on the market. The innovation is happening very quickly. Therefore, there are many different module types and material compositions, so it's very hard to come up with one standardized recycling process that would work for all of them, because each module is a tiny bit different. Second challenge is that currently the recycling is very costly. It is also caused by the PV waste stream not being that high currently, but the waste will increase very drastically in the future. According to Irene, this number will be as high as 60 to 80 million tons of PV waste globally in 2050, I think I said that. And the third challenge is the design. If the recycler doesn't know of what is in the module, it is hard to recover these materials. So of course you need to know the material composition, and some materials present a bigger challenge than others. In the end, it's possible to recover many things, but it is important to first be aware what's in there. So this is kind of the state of the art, and now I want to tell you a little bit about two projects that I'm involved in, and those are EVERPV and RESILEX. So EVERPV is an EU-funded project that has three big objectives, recovering three types of materials with 99% purity, and that is glass, silver, and plastics. Also, this project will come up with two new delamination technologies, and also it has many targets, for example, for recovering 1,000 kilograms of this very pure glass, but also of producing 10 brand new modules that use these recycled materials stated above. So it is also about creating a brand new module. This is a little bit about what are the recycling technologies applied. So this project is recovering silver, the plastic component, and the glass. However, there are many projects that are focused on recovering silicon. So the project will cluster with these other projects to kind of create an integrated recycled product. The delamination, the two methods that I mentioned are optimized grinding process and infrared irradiation. and 2 delamination lines are being developed in France and Italy. Then after the purification is applied, this project will demonstrate the potential reuse of recovered materials and business case of open loop recycling or closed loop. So we want to reuse these materials in new PV modules, but also in, for example, flat glass and packaging glass. And also manufacture 10 new solar modules. This is the consortium. You can have a brief look. Many great partners in there. And then we have another project which is called RESILEX. And the SI can already tell you that this one is about silicon. So this project is connected to also the mining sector and to batteries, but I'm going to focus on what are the objectives of this project for PV. So first of the objective is to reuse silicon, so to reuse kerf for ingot production. Then another goal is to recycle PV modules, so recover silicon and apply it in PV and batteries using 2 methods, which are froth flotation and electrostatism. And then also design new, more recyclable products in mining, in PV, and in batteries. These new products are focused on, when we talk about PV, on reduction of indium content, on reducing silver content, and using new materials for module encapsulation, which would be recycled better. Here you can see kind of the goals a little bit more clustered. So we have some critical raw material recovery from waste. Second one is the PV activity. So we have the solar modules recycled. We have the recycled PV modules and the recycled kerf. And the ingots grown from the recycled silicon, and then the production of new wafers and the new solar cells. And then the third stream of work is the anodes for batteries. So from end-of-life solar panels, there is a new process being tested for silicon-based anodes. And this is the consortium of the project. And that's it.
Thank you, Daniela, for the presentation and the very insightful information that you gave us. So if I can summarize a bit what we discussed about the need of PV recycling, I would say that it is the environmental benefits, it is the critical raw materials independence, and it's also the economic factor. And it's really interesting that we already have these projects that are developed at the European level. It shows that even though we are not at a point in time where the need for recycling is dire, we need to plan ahead. And because we discussed about 2 projects, I would like to pass the mic to Carlos, and I would like to ask you to tell us more about the project that you are currently coordinating that has a similar sort of approach to end-of-life panels.
Yeah. Yes, thanks, Irene. Thanks for the organization. It's a pleasure being here today. Thanks again. I'm going to present very briefly the retrieve, but this project is quite similar. Actually, it's one project, sister or sibling project of yours. We are working quite closely and interacting because it's in the same line of recycling. If you don't mind, I would like to stand up also, because it's quite unpractical to see the screen from here. So, the retrieve. What is the retrieve? The retrieve is the reintegration of photovoltaic panels, the waste, back into manufacturing of high-value products. This is coordinated by us at the Institute for Energy Technology, by me and my colleagues Rune and Duygu. I am, let's say, the person that is in front of the European Commission, so the first slap when it comes to finances and so comes to me, but the people that really knows the business are these 2. Rune on the photovoltaic value chain and Duygu on the recovery of materials. So I'm just, let's say, the meme in front of the Commission. So what's the retrieve about? Check this out, the Eiffel Tower. So beautiful, isn't it? No, it's really a piece of art in Europe. Well, it happens that by the year 2050, and that's why I place the Eiffel Tower here, because for me it's somehow a huge mass of ferric scrap, if you want. By the year 2050, the equivalent to 700 Eiffel Towers per year worldwide will be end-of-life photovoltaic panels. Can you imagine what it is? The Eiffel Tower is huge. That's why I took this example. No need to say that we have French partners that perhaps are not that excited that I put this Eiffel Tower as an example of scrap, but I think it's very easy to understand for everyone. That's the volume we are going to talk about. 700 per year worldwide. And this is something that we have to process. Otherwise, we will convert the whole Europe in a huge landfill. That's the last thing we want. So, as a response for this challenge, we have developed the Retrieve. The Retrieve, what it's going to do is develop circular economy approaches to bring these photovoltaic modules, let's say the components, the basic components of the module, back to photovoltaic. So, instead of doing this, we are going to make photovoltaic panels. This costs nothing. A photovoltaic panel costs a bit more. So this approach is going to be addressed using a number of technologies that are quite advanced, that we are still developing, but by the end of the project, hopefully we will reach a TRL 7, so it's full demonstration and full production of photovoltaic modules, first made in Europe, hopefully before than you guys in the other projects, and totally from scrap. So let me, besides that, besides the fact of the huge volume of waste that we are going to face in the European Union, or worldwide if you want, let me present the other challenge that we are seeing. The first one, of course, is the waste, but the second one is the external dependence. Here we are talking about Europe that is resilient, that can tackle the energy issues that we see in the future, that is fully decarbonized when it comes to energy production. But then it happens that almost everything is done in China, so our dependence is huge. As a nice example, we put this figure in the project where it's very clearly observed the huge dependence that we have in China for the main components of the photovoltaic module. I would try to dare you to find Europe there in one of the different items: polysilicon, wafer, cell, or module. Europe, I don't know if I can even see it. Should be, yes, here. In the wafer, this 0.5% is Europe. Woohoo! Fantastic. Yeah, the other 90 a lot is China. Right? So this is exactly what we want to break in the Retrieve. We fully understand that China has been flooding Europe with photovoltaic modules, with photovoltaic panels. That's wonderful because now we have panels everywhere, but in 25 years' time, this will be a huge amount of scrap. So the Retrieve, what wants to do is, if you want, let's call it urban mining. We are going to use the panels to build up our new panels.
If I may intervene for a second, 25 years in an optimistic scenario, because we have repowering, we have a lot of panels that are being broken due to weather conditions that are going to reach end of life earlier. So, yeah.
We see a lot of panels already hitting the recycling market. We have one of our partners, for instance, Total Energies, called us one day and said, Carlos, we are going to dismantle a full photovoltaic park. I said, okay, how much are we talking about? I said, not too big, 3,000 panels. Can you guys take it at IFE? I mean, IFE is big, but not that big, I think, Rune. So we were supposed to process a relatively small photovoltaic field from Total Energies with 3,000 modules. We just don't have capacity to go for that. Not even our dismantler in Spain has capacity to dismantle such a large amount of modules. So these are the two main issues. First of all, the waste, second, the dependence. So our approach, or what we tried to sell to the European Commission and we sold successfully, is that the solar panels are many things, the end-of-life solar panels, but never a waste. The solar panel is not a waste. The solar panel is formed by an aluminum frame, glass, a polymer, the EVA, then you have the solar cell, that this is the silicon. Again, we have EVA, the backsheet, and the junction box. The waste directive that regulates the electronic and electric components and equipment, the WEEE, has said that the photovoltaic panels, the end-of-life photovoltaic panels now are into this directive. So that's extremely good, because now there is an obligation to recycle them the same way we recycle a TV, a mobile phone, or these kind of things, okay? But what's the trick here? The dismantlers have realized, and it's very obvious, that, well, the target for recycling of the modules is about, I don't remember exactly, it's 80–85%. But the dismantlers have realized that just taking out the glass, taking out the aluminum frame that goes to make Coca-Cola cans or whatever, and the junction box that is plastic and copper, they already hit the target from the directive because it's heavy. But what happens with the rest? Some countries are landfilling, some others are incinerating. And these things sometimes contain heavy metals and things that are, one can say, a bit nasty. And it's really the last thing that you want in the air that we are breathing each day, okay? So we said, yeah, that's fine. The waste directive is fine, but the retrieve goes much further. Our target is 95% of recovery on all the materials, leaving only for, let's say, for a non-reintegration into photovoltaic panels, only the polymer fraction, that I will show you later how we do. I think Daniela also mentioned the composition that we have. In the majority is glass, aluminum, silicon, copper, but we are particularly interested in silver. The new panels perhaps do not contain that much, but the old panels really contain an insane amount of silver. And, well, we all know that silver is something that we may want to put somewhere else than in a landfill. That's why my colleague here, Duygu Yilmaz, is developing technology for the recovery of silver. But not the regular one of soaking in an acid. We are doing something through reagents that can be regenerated so that we minimize the emissions related to the silicon recycling. Duygu will explain a bit more in detail how we do it. So which are our solutions and impacts? What do we want to create here? Basically increase the circularity and total reincorporation into the future modules. So which are our objectives? New scrapping processes and new dismantling processes to separate the different streams of the photovoltaic modules so that they become easier to recycle. Because the challenge nowadays is that the dismantlers are kind of crushing the full thing so that it becomes a nasty mixture that is impossible to recycle. So here our dismantler in Spain is going to develop a technology to try to separate in a clean way the silicon from the glass, from the plastic, and so on. We will purify 95% of the materials to meet the photovoltaic market, not to do anything else. We are not interested in glasses, in bottles, in windows, no offense. But we are interested only in bringing it back to a photovoltaic module. That's why we have a quite solid partnership to achieve this target. 99% of the glass and 98% of the silicon will be recycled and reintegrated back. So virtually no disposal of these two critical components of the panel. And the most important thing, and something that was praised by the reviewers, fully made in Europe. We are not externalizing any step, we will do it here. Our partners need to find a way to do it here. Silver, 99%, so virtually total recovery of silver. We don't want a single atom to go into the waste. And besides of that, the toxicity provided by the antimony or other potential elements in the panel will be removed through the processes that Duygu and her team are developing at IFE together with the partners. The residual plastic, this was very challenging. The residual plastic cannot be reintegrated back into the production of new photovoltaic modules. But for this guy, what we have developed is a process that will convert the plastic into syngas, a valuable mixture from which we can do, for instance, methanol and introduce it later on in fuel cells or in other applications for decarbonized mobility, for instance. Besides that, this is, let's say, the technical layer of the project. We have a very solid bunch of activities, a specific work package dedicated to the development of new business models. And within these new business models, we are even going to create a secondary marketplace. So all these streams will be, we will be able to trade them in Europe through this marketplace. Besides that, our friends in RPIA are supporting the project a lot for the political interaction, for the creation of roadmaps, and for the understanding of the policy framework out there. Our partners, how we do this? This is an extremely ambitious project. This is an innovation action from the European Commission with approximately 9 million euros in total, 7 million of which are coming directly from the Commission. The rest are CERI, that is the Swiss research agency, plus the own contribution from the partners. We are going to lift from TRL 5 to TRL 7, so this is a pilot demonstration in a relevant scenario, and we will implement it during 42 months. And if you check the partnership, we have a fantastic, this is something that makes me very happy and very proud, we have a fantastic distribution of the, or a fantastic representation of the European continent, from Norway, where the IFE team is located, down to Spain, Romania, Turkey, and now even Ukraine. Because through this project, one of the satellite competences that we want to do, or satellite activities, is to help our colleagues in Ukraine to reconstruct the energy system through the recycling of the panels that have been damaged. So we are not only responding to, let's say, to the technical components of the call, we are supporting something else. In total, we have 19 partners from 10 different countries, and we have all the possible profiles that we need to implement this action. We have the owners, operators, and dismantles of photovoltaic fields, scrapping companies, suppliers of research and development, so basically research institutions and universities also for the capacity building. We have manufacturers. We need people to dismantle, and we need people to reassemble the stuff, so the manufacturers are here. Business developers, and the public administration and associations like RPIA and your sibling association, ASEU in Ukraine. So, having said that, I would like to hand over to my colleague Duygu that will describe exactly, or well, approximately, we cannot disclose much because of the IPRs, how we are doing the glass and the metal and the plastic valorization from the panels. Duygu, floor is yours.
Thank you so much. I hope you hear me there.
Yep.
Yeah, perfect. I can introduce myself first. Yeah, my name is Duygu Yilmaz, and I am one of the technical coordinators of RETRIEVE, and I'm also leading Sustainable Minerals and Metals group at IFE. Can we see the slides?
We can see the slides in the...
No. Duygu, I will share myself from here. You tell me next, and I will show the screen.
Yeah, okay. Then I can, yeah, exactly. Now you see, I guess. I will, Daniela introduce most of the challenges actually, but I want to add what is also most challenges when we talk about the closed loop recycling. We know that some of the end-of-life panels come broken to the disassembly facility. Some of them are not broken, intact. And this is one of the challenge when we develop a recycling process. This is the first thing. And when we talk about closed loop, we don't have any regulations in neither like silicon industry nor glass industry about the secondary raw materials regulations or the target specifications. We don't know what to use, what to not to involve. For instance, we know that technology changes all the time, both in glass and silicon, and there are some impurities in the system where we don't know if there will be a problem or like we need to reduce the amounts or not. So we are also working on it. This is very important. And when it comes to glass, we know that we will need to tackle both the intact glass and the broken glass because it comes different. And we have a technology where we can also utilize the intact glass coming from the disassembled facility, so to say, after certain cleaning and conditioning. And we think that it's very relevant to have utilized this intact glass in new panels, even though the dimensions and the regulations will be a bit maybe different for the new panels, but we have a roadmap for this now. And when it comes to the broken glass, this is very challenging to utilize them in the new solar panels, but we have also a plan for that, and we are developing a new technique where we can utilize the broken glass to produce new solar glass as well. And we have already applied to one patent from our project, and the other patent is on the way, I can say. We can change the slide if you could. And yeah, so when it comes to metal recovery, yeah, this is also a very important topic, as both of the speakers mentioned. And silver, even though it's not as an amount, it's not too much, but the value is huge. So we know that the silver recovery needs a lot of attention, but it's also important to go a bit beyond the state of the art, because we need to avoid using the traditional let's say process chemicals, where we need to tackle with the disposal and also the other hazardous emissions when we are trying to, let's say, recycle the panels. So in our project, we are recovering silver, yes, and we are doing it with environmental friendly chemicals, so to say. And we are also targeting 60% of the process chemicals recovery via regeneration, because this is very important when you need to deal with the huge mass of, let's say, waste, and we don't want to call it waste anymore. So that's why we are targeting the reutilization, reuse of the process chemicals. And it's also super important for us to be able to adjust this process to the, let's say, to make it feasible as much as possible. And let's say if you receive intact panels, you should be able to apply this process to recover your silver, and if you get it broken, it should be also working. So we are also targeting to increase the flexibility of the process. And it's also important to say that we have very important progress in the safe disposal of the metals, heavy metals. We are not only considering recovering silver, but we are also taking care of the heavy metals. We can change the slide. And the last part that I want to talk about is the plastic valorization. As I mentioned, the technology changed a lot, so we know that there will be some different compositions in the plastic or the, let's say, used materials. So we are trying to process, let's say, very flexible pyrolysis method, where we will be able to utilize all of the different, let's say, technological panels. We will do this pyrolysis process, and we will get some, let's say, subspecies. The target is generate syngas out of this pyrolysis process, but we are also targeting the producing of the subspecies like methanol or other olefins to be able to close the loop in the future. So it will be very important roadmap for us to know what kind of, let's say, different plastic fractions we will be able to deal, and also how we can close the recycling loop after the, let's say, recycling. That's it from my side. Thank you so much.
So then perhaps we... Yeah, sorry. So now we can move to the last part of the project, that is the recycling of the silicon. That was it's a very tricky substance to bring back into photovoltaic. And to describe this, we have our own expert, that is Rune, Søndenå. Here you are.
Good afternoon. Can you hear me all right?
Yes, we can hear you.
Perfect. Yeah. So as Carlos said earlier today, we have two problems coming up. A big mountain of waste to handle, and also silicon is covered by the Critical Raw Materials Act for one reason and one reason only. Almost 80% of all the silicon produced is produced by one country, and that is China. So closed-loop recycling, bringing end-of-life silicon back into the PV is an elegant solution, could potentially solve both these problems, creating an alternative stream of the material, and also then bring in a market that can absorb the amount of waste that will be generated. And like Daniela said, there are some technical challenges for doing this closed-loop recycling, and I will expand a bit on these challenges. Next slide, please. Yeah, so this is an elegant figure made by Hanwha Q-cells, and I really like this graph because it shows my entire career in the PV industry. I started working on aluminum back surface field in 2009, so this learning curve, it shows the evolution of the PV industry during my entire career. What we see here, every single point in this graph represents a small improvement, if it's a tweaking of the process parameter or improvement of the raw material quality going into the process, or some tiny improvement, and over time it really adds up. So it's a very nice improvement, and also it shows the transition from each cell type. See that the aluminum black surface field in black, when the improvement started tapering off around 2014, there was a change to the new solar cell type. The PERC cell took over, and later in 2020 the TOPCon solar cell architecture took over. And this represents part of the problem, part of the technical challenge. The solar cell you buy today is completely different than the solar cell that was sold 15 years ago. It's generations ahead, and the quality requirements for the material going in is quite a bit higher than the requirements 15 years ago. So when we're talking about closed-loop recycling of silicon, what we're really talking about is upcycling. We really need to improve the material quality during this process. And that is half the challenge. Next slide, please, Carlos. Yeah, so the second half of the problem. We have, in addition to the gradual improvements we saw on the last slide, there is also quite a few rapid shifts or change of technologies in the PV industry. Especially in the last few years, we've seen a lot of them. The multi-crystalline market disappeared more or less overnight. That was super fast. See that gallium is replacing boron as the main dopant in P-type silicon. And the change we are seeing right now is that N-type is replacing P-type silicon as the dominant technology. And the common denominator here is that every one of these changes happened so much faster than we expected. When the change came, the industry had to adapt very, very fast. And this is also a challenge, because it means that we need now a different technology than what was used 15 years ago. And typically boron is a challenging dopant to handle and to get rid of. Yeah, next please, Carlos. Yeah, so it is absolutely possible to completely ignore the challenges and go for a simplified recovery of silicon, direct remelting of the end-of-life silicon recovered into the process. And we see that Trina Solar has attempted this quite recently. They are able to produce a solar module, state-of-the-art solar module with a 20.7% efficiency. At the same time, their main product with virgin polysilicon used has an efficiency of 22.5%. So, and it may not seem like a lot, but this difference, that's 10% reduced energy production, and modules can operate for 10, 15, 20 years. So this is quite a reduction in energy production, and I don't see how this can make sense in any financial way at all. So it's interesting that they tried, but it's hard to defend this method financially. Again, next slide, please, Carlos. That is the method we are trying in our projects in Retrieve. We don't really believe in the direct remelting of endolyzed silicon. The penalty that comes with this method, partly because of the quality, is not good enough, and partly because of the dopants that are present, simply makes this, well, we believe this is impossible to achieve during the direct method and the simplified method. We believe that we really need an upcycling process to be included of the material. We need an additional purification process, and we are planning to test the chemical purification process, running the end-of-life silicon through that's just a conventional production route for silicon. And it will be exciting to see if we succeed, and if we manage to do it in time to be the first. We have high ambitions, and we also realize now that it would have been nice to track boron-doped silicon, and having a digital product passport going back 10-15 years would have been great. I guess implementing it now is not perfect, but it is a good solution, and we might need it 15 years from now. Yes. Thank you, Carlos.
So thanks a lot, Rune and Duygu. Just to conclude, let you know that the Retrieve is in the social media also. We have created our own website that is here, retrieveproject.eu, and we also have our profile in LinkedIn at Retrieve Project. So if you want to know more about the project, exciting developments that we are doing, our participation in the different networks, and our contribution out there in Europe from the Retrieve with our perspective, insights, and so on, just go into the LinkedIn, follow us, and stay tuned to the new paradigm on recycling of photovoltaic modules in Europe. Thanks a lot, everyone, for your attention.
Thank you everyone for the very insightful discussion. So you are developing a technology that's going to be suitable for basically every type of PV panel, regardless of how old they are, right? Because you mentioned that PV panels that were developed 15 years ago are different from what's happening now. So it's going to be...
Yes, they are radically different. They have nothing to do. So somehow what Duygu and Rune also mentioned is that the technologies that we are developing here should be able to accommodate these differences. That's why in the Retrieve we have a dedicated set of experts from Fraunhofer developing analytical tools so that the panel can be characterized as soon as possible and give us inputs about what we need to do. So somehow we will need to sort out the different panels and follow the recycling processes according to their characteristics. But the idea is yes, that the process should be able to accommodate most of the modules that are expected to flow into the recycling facilities. For the panels that were operating or have been operating for 20 years, it's complex, perhaps was a mix, and they come extremely damaged. But from now on, we will have a much better tracking system for the type of panels that are entering the market, and therefore we can fine-tune the techniques and the technology that we are going to develop so they can accommodate the panels as they come, regardless of their nature.
That's great to hear, because there are a lot of projects that are going to, a lot of PV parks actually that are going through repowering, and because you cannot replace the modules and the panels that were used in the past, you cannot find a similar solution. It's great to hear that they have a way of being reintegrated. So my take from this whole discussion is that in practice things are developing at a really high pace. But now we need to work on the legislative part.
Yes.
And we need to have standards, new standards for PV panels, and maybe a dedicated piece of legislation only to them and for them to be reintegrated. And I think it's also very interesting that you support this manufacturing sector that's very discussed at the moment. It's made in Europe, so we are really looking for...
Shall I comment?
Please do.
Yeah, well, we are about to sign the grant agreement with the European Commission of a new and even more exciting project where, again, I have the pleasure to count with our friends in RPIA, Irene and Adriana. This project is called Empower, and it's the second phase somehow of the retrieve. I also have the pleasure to coordinate it together with my colleagues. In this case, Duygu, you are a bit involved, but it's mostly Rune from photovoltaics. The Empower is about photovoltaic manufacturing in Europe, and this project is twice the size of Retrieve. It's 20.5 million euros. So what we are going to develop in the Empower is new and radically different technologies to manufacture the photovoltaic modules. It's quite clear that we cannot compete with China when it comes to the manufacturing lines that they have, because they are extremely efficient, they are very cheap and so on. So the European Commission has decided throughout this call that we want to develop novel processes. There is not much that I can say yet about the process themselves, but trust me, they are really mind-blowing. We have one of the partners in the retrieve mentioned, and I think he's right, the panels of the future perhaps will not contain much silicon anymore, because we are going to operate with extremely thin layers of silicon. So the silicon will be almost nothing. So this stream perhaps doesn't need to be valorized and becomes just a trace pollutant within the glass fraction. I cannot mention the name of the partner or the technology itself, but this is coming.
For
and
the
in
moment,
3 years,
but for the next iteration of this workshop, when we'll have more results.
For the next iteration, perhaps I can mention the name of the partner. But the technology will be tricky to disclose. But these guys are really going to face or somehow to tackle the incredibly high productivity of the Chinese factories, developing something radically different here in Europe. So this is Empower. Will come in, hopefully in 1 month, if everything goes fine. We cross fingers.
Follow the LinkedIn page and you'll know when it will come.
Follow us or follow us in LinkedIn and you will see.
Yeah. Thank you for mentioning it. And I think it's very important to bank on what we can do as Europe, and that's innovation. We are, even though we cannot compete in terms of manufacturing, we can compete in terms of innovation and new ideas. Now, I would like to leave you with the conclusion that solar panels are not waste. They are and can be reintegrated, and they are going to be the panels of the future are going to be the panels of the past.
Exactly, yeah, very good one, very good one.
Yeah.
Fantastic, yeah.
Thank you everyone, because we're running quite short on time. We won't be taking questions, but I invite you to connect with everyone that was present on this stage, both from Retrieve and from SolarPower Europe, RESILEX, EVERPV. And keep a close eye on what's happening, because even though at the moment it's not that big, in the future we are going to see panels being recycled everywhere. Thank you everyone. I hope you enjoyed the first day of the PowerShift Summit. And of course we welcome you tomorrow at the same time, the same location. Thank you.
Thanks.